We actually have a patent pending on a technology that involves using batteries on the bottom of the aircraft that actually are jettisonable. And there's two versions of it. One is actually that the bottom of the aircraft contains what is basically a glider that is nothing more than batteries. And then when we jettison the batteries off of the aircraft, they can be remotely piloted back to the airfield and landed as a glider. And well, most of our energy in an aircraft is used up during that climb segment, that takeoff and climb segment. We really use up a lot of our energy. These kinds of aircraft that are very sleek, low drag profile aircraft, once we're up and cruising, you know, they're basically gliders. And so it uses very little battery energy once we're actually in the air. And so if we can tow launch, like with this aircraft, where we can either tow it behind a car or tow it behind a regular aircraft, get our altitude, and then save what batteries we do have for the actual process of cruising around and using them when we're not soaring or thermaling or that kind of operation. The endurances, even for 100 pounds of batteries, can be quite substantial when we're talking about a very low drag aircraft like this.
What's your performance goals for it?
Well, there's a famous saying in aviation that we talk about all the time, and that is that paper airplanes fly great. What basically that means is we can design the stuff and we can come up with all kinds of numbers and blow smoke up your skirt, but it isn't until we actually get out there and prove that the numbers really mean anything. And so we try not to do that. We have a couple of design goals that we're working for. We're structurally designing the aircraft to meet a VNE, or a never exceed speed, that's well over 100 miles an hour. Our actual target VNE speed that we're shooting for is 130 mile an hour VNE speed, which is fairly substantial. That's for this size aircraft, that's really a pretty substantial number. The ultralight rules require us to not have a straight and level speed of more than approximately 55 knots here. And that, when we fly it as an ultralight, what we end up having to do is pitch the propellers primarily as a climbing mechanism. And then once we're up in cruise, we're soaring around, and we'll just use the propellers for low speed flight and stuff like that. But in a experimental amateur built aircraft, those cruise speeds can be basically unlimited. We can really cut the thing loose. So we're kind of designing the aircraft, one aircraft that will eventually meet two completely separate flight regimes. And so at this point in time, we're shooting to operate it as an experimental. This one will be actually experimental research and development, because it's not legal to build this aircraft as an experimental amateur build, because it doesn't meet the qualifications, simply because we're building it solely for the purpose of eventually selling parts and kits. And so that puts us in an R&D phase. So we won't have any restrictions like we do on a Part 103, but at the very same time, we are building all of the components to be able to meet the requirements for that Part 103 operation. And this rabbit trail that I went off on here all came back to this whole concept of getting an aircraft light enough where we can have some batteries useful. So even if we don't end up being able to get a resolution on this batteries being part of the empty weight and being able to use as many as we want, we still believe we can put the airplane into that category. The flight durations will be much limited by that, and only time will make that better as we get battery technology that improves.
Right, okay. So what are the, when do you anticipate being able to have it finished and begin doing your initial, I would assume you're going to be doing some tow tests, taxi tests, things like that. So when does that happen? What's your target?
Our target is for the first of the year, so coming up pretty quickly here. Probably February, I would guess. February, March, I think it'll actually be in the air flying. That's our goal. And I've built many airplanes, so I kind of have a realistic idea of what it really takes to do this. And it's kind of like remodeling your house. Double the price and add 10%, and you're probably pretty close to your numbers.
Right.
What challenge though on a new aircraft?
Yeah,
like
where are you at, do you figure, percentage-wise? You're about 50% done with it at this point, or?
Well, the design process is basically complete at this point. So now we are basically taking the existing design that we've done. It's all designed on SolidWorks, and every single part on the airplane is built using SolidWorks and a machining process, SolidCAM, and all the parts are CNC manufactured, pre-matched drilled holes. The goal is eventually to get this to where it's a relatively simple process to build the aircraft. And so a lot of our time and energy at this point is going into, we're not building a one-off aircraft, we're building a production line, and we're building molds for all the carbon fiber components, and that's really where the biggest time, you know, if I just wanted to put the airplane together and I didn't have to do all of this production stuff, oh, even in 3 months I'd be looking pretty good.
And looking at the design, looks like what you're doing is you're doing a sort of a prone position for the pilot rather than a sort of this classic seated position. Why did you choose that, and do you think that's going to help or hinder the adaptability of this?
Well, you know, there's actually some military studies that were done on flying in the prone position, and they actually weren't very favorable. However, and by the way, this is by far the most controversial part of the whole design is the prone position on the aircraft. Now, if you talk to a hang glider pilot, of course, that's they don't even understand why anyone would be concerned about that, because that's how all of them fly. I think that's just a natural part of the process. So we have to, we kind of have decided that's what we're going to stick with. There's a couple reasons for it. Number one, we've gone through several derivations on the design. In fact, on the website, you actually see kind of the process and our thought process, how we got to where we are now. But because the pilot is basically the same weight as the aircraft, the position of the pilot directly over the center of gravity of the aircraft becomes paramount. All of that moving the pilot off of the center of gravity just costs us structurally. And so in order to simplify the design, we haven't figured out a way that we could build a Part 103 legal aircraft and get the pilot seated upright. There's several other elements that would have to take place. One, compromising crash survivability, and even you know, even if you're not talking about crashes, and we certainly never you know, want to be thinking that that's what's going to happen, but you have to think about an aircraft. You know, an airplane where you're just sitting out in front of all of that structure, and then something does happen, you know, you're the brunt of that impact, and that, in my eyes, is not an acceptable way to design an aircraft. So we've built in a lot of safety features into the airplane. We actually kind of do it similar to what the car manufacturing companies do, where we have a really strong crumple zone underneath the aircraft as well as in front of the aircraft that's designed specifically to absorb any impact loads. You know, it's impossible to have built any airplane in the history of aviation and not had a crash at some point in time for God knows whatever the reason is. But the potential hazards really get reduced when you actually plan for that. And there's lots of airplanes out there right now that have to sacrifice that safety in order to be able to get the weight of those aircraft down. And we just decided that that was one of the areas where we didn't really want to compromise. Keeping the center of gravity right where it's at, keeping the low profile. By the time we sit upright in the aircraft, if we're sitting over the center of gravity, that just raises the total height of the aircraft to the point where we really take a significant penalty in drag. And so this actually allows us, we're actually straddling the main fuselage boom tube like we'd be riding a horse.
Right.
And we're sitting right down as low as we possibly can, and we've got some cutouts for our arms so that we've got some ergonomic comfort in the front end of the thing. And I recognize that there's only one way really to overcome the stigma attached with that prone position, because everybody would like to think that they, you know, want to sit in their lazy boy while they're out there cruising around in the air. But we're just going to have to prove to them that it's a comfortable position and show the performance on the thing. And that's where the bottom line falls.
Yeah, let's talk about safety now. I noticed in looking at the website, are you going to have some type of ballistic chute capabilities on this then as well?
That's actually built into the design on this, and it's also the main spar section of the aircraft, right where the pilot is centered over, where he's actually seat belted into the aircraft, and that's also the location for where we attach the main ballistic parachute. BRS, Ballistic Recovery Systems, is the primary supplier for all these ballistic recovery parachutes. And one of the nice things about the Part 103 FAA regulations is it allows us to put in safety devices such as the recovery system, and we don't pay a weight penalty for doing that.
Oh, okay.
And so we get to add that weight onto the empty weight. So the structures in the parachute and all of the mounting equipment necessary for that all get, we get to use part of that in our empty weight.
Coming back to the control part of this, are you going to be using a stick, a yoke? I mean, how does, you know, and having this thing out in front of me like this, you know, instead of between my legs. So I'm wondering about, you know, how you're going to handle the mechanics of you know, elevators and ailerons and things like that.
It's conventional controls, just like you would have in a conventional airplane, where we have a yoke with some controls that are on that.
Okay.
But we're flying it like a conventional airplane. The rudder pedals, however, because you're in the prone position, are actually on the back of the airplane. So your feet stick down the boom tube and actually fit in there. But that's an interesting part of our whole concept that we have here. The aircraft is actually, I have a couple of pretty smart guys that are working on some control system development using what's called an Arduino. That is the control system that we use for these little model flying platforms that you see out there hovering around.
Right.
And this Arduino just uses basically the same kind of technology in your cell phone with these little gyros that allow the airplane to be able to hover and do thrust vectoring and control, thrust control on all of these different motors on the thing. We have identified that we will be able to, using this technology, control the two motors in such a fashion that we will basically significantly reduce the amount of rudder input so that we can actually control the thrust vectoring to maintain perfectly coordinated flight, and even to the point where we can operate with a two-control system, ailerons and elevators, and someone that was a paraplegic could fly the airplane and not even need the rudder whatsoever, and not even have to couple it in there, but as so much as just using thrust vectoring motors to be able to control yaw of the aircraft. And that's already been done on several of the large electric aircraft that are currently flying. They actually fly directionally using thrust control.